Now, let's talk about the potential dividers and potentiometers. We have many types of potential dividers. You can divide the voltage using two different resistors like this. We have two resistors here. If the voltage is 12 volts and we have two resistors in series, and this resistance is 2 ohm and this resistance is 4 ohm. So the voltage will split in both resistors. That's here we have 4 volts and here we have 8 volts. And the total is 12 volts. Let's try solve this. We have a total resistance of 6 ohm because these are connected in series. V equals I multiplied by R. The voltage 12, the total resistance 6, the current is 2 ampere. So here the voltage in this resistor is V equals IR, which is 4 multiplied by 2, which is 8 volts, and here the voltage equal the current, which is 2 multiplied by 2, which is 4 volts. So it is the simplest way to have a potential divider. We can make it better using a battery and two resistors. One of these is a variable resistor and the other is constant resistance. So if you have here, let's say 4 ohm, and this variable resistor can change from 0 up to 4 ohm. And here we have, let's say 8 volts, okay? If the resistance of the variable resistor is 0, so 8 volt, all of these will go to the 4 ohm. If the resistance of the variable resistor is 4, so the voltage will split for 4 volt and 4 volt. This is a very nice way to change the voltage given to the variable resistor or the device. So if you have here a bulb, this bulb will have the same voltage as this resistor. So if this resistance is 0, 8 volt will go to this resistance, and which is equal to the voltage through this bulb. And if you want to make the brightness of this bulb less, you just increase the resistance of this variable resistor. Another way of changing the distribution of voltage, we have here a constant resistance and we bring a variable resistance wire, variable length. This is wire and this movable point, so you can move this wire up and down, okay? If this wire in this point, let's say it's point A, so the current will pass through smaller path like this. So here no resistance, so all the voltage will given to the constant resistance. If you move this wire, let's draw another one, it's better. We have a battery, we have a wire, resistance wire, like this, and this is the sliding contact, and this is the variable resistor. So if we put the sliding contact at B, so the current will pass through a longer path. So we have larger resistance because we have longer length, okay? We have here a longer length, so higher resistance, so the voltage will split in both of these resistors. Another way to split the voltage using a thermistor. We have a constant resistance thermistor like this. If the temperature of this resistor increase, the resistance of the thermistor decrease because it is made of semiconductor or semiconductor, okay? So increasing the temperature, this resistance will decrease. So the reading of this voltage here will be less than the voltage here, but the total of these V1 and V2, the voltage have to be equal to the electromotive force. We can also use a light-dependent resistor connected in series with a resistor. If the light intensity increase, the resistance decrease, so the voltage through this resistor will decrease, and the voltage will split, and this will take more voltage as the light intensity fall on it increase. So this is the story of the potential divider or the potentiometer. So we can split the voltage equally or depending on the value of the resistance. How can I find the value of the output voltage from the circuit? We can use this relation, which is VR1 over R1 plus R2. Let's see how can we use this relation. If we have here an electromotive force, and this is resistance 1, and this is resistance 2, and we want to find the output voltage here. So V1 equals R1 over R1 plus R2 multiplied by E. If you want to find the value of R2, you just put R2 here, okay? So this is the ratio of voltage given to this resistor from the total electromotive force of the battery. Now, here we have a battery, and we have here a potentiometer, which is a wire of about 100 centimeter length, and this is the movable point. We can move it forward and backward. We can use this way to find the value of unknown electromotive force by put the circuit in this way. A potentiometer can also be used as means of comparing potential differences. The circuit on figure 20.22 illustrates the principle. In this circuit, the variable potentiometer resistor consists of a length of a uniform resistance wire, this, stretched along a meter rule. We have a meter rule, and we put a wire on it. We will see like this in the practical sessions. Contact can be made to any point on this wire, so this can be moved for right or left depending on the experiment, and depending when you find the value of the reading of 0 here. Contact can be made to any point on this wire using sliding contact. Suppose that the cell A has known EMF. This is known. The cell is switched into the circuit using the two-way switch. Okay, this is the two-way switch. You can switch this battery or this. One of these, you can't connect both of these together. The sliding contact is then moved along the wire until the center 0 galvanometer reads 0. Okay, so the length LA from this point to here of the wire from the common 0 end of the sliding contact is noted. Cell B has an unknown electromotive force. This cell is then switched into the circuit and balancing process repeated. Suppose that the position at which the galvanometer reads 0 is then a distance LB, which is longer than LA or smaller, whatever, from the common 0 to the sliding contact. The ratio of EMF is the ratio of the balance length, that is EB over EA equals LB over LA. So I can compare the value of electromotive force B over electromotive force A to the length where the current is 0 through the galvanometer over LA. Okay, so knowing this length, knowing the amount of EA, you can find this value, or you can write the equation like this: EB equals LB over LA multiplied by EA. Known, measured. This can be calculated easily. Okay, Here we have a potential divider using a variable resistor. Now, here we have a circuit connected with 3 resistors. You can find the value of the current or voltage of each resistor. You can calculate the power also. Okay, please solve these questions from this book, and we have many more questions about Kirchhoff to be calculated. Let's talk about this relation between EMF and internal resistance. We have here the battery internal resistance. We have here the load resistor. Okay, if we draw the relation between the voltage against current, we will have a reading like this. Okay, the maximum value of voltage that we can have is the EMF. So this value is the EMF. The gradient of this line is equal to negative R. Why? Because EMF minus IR is equal to the voltage of the load resistor. Okay? Now, we can take the relation like this. Let's take another color. I is in the x-axis, okay, and V on the y-axis. So if we rewrite this like y equals mx plus c, y is the voltage, m is negative R, x is the current, and the y-intercept is the electromotive force. It's a very important relation. Again, when we deal with Kirchhoff law, we have to be careful about the directions or the movement of the current. Okay, how? New page. If we have a battery and resistor here and resistor here like this, and this is the main current, which is I, this is I1, and this is I2, this R1, R2, and maybe we have internal resistance or not. It depends on the question. So here the main equation, that's it's I1 plus I2 equals I, which is known from Kirchhoff's first law. Now, the current will pass through this path. Some of the current will split and some to this branch, and it will back from here. So here the current is I, here the current is I1, and here the current is I2, and here is I again. Okay, we can take this loop, which is loop number 1, and we can take this loop, which is loop number 2, and use Kirchhoff's second law to find the value of the current or voltage in each branch. We know that the summation of a electromotive force equal to the summation of potential difference through closed loop, as Kirchhoff's second law said. Okay, so using the first circle here, we start from this point, which is a junction, and move through this path and back to the same point. Okay, while we are moving in this path, we have here an electromotive force. We write E, it's equal to, we have current I here, I, but we have no resistors through this path. So we multiply by 0, plus we continue here, we have the current, which is I1, and we have R1. Okay, this is equal to 0. So we have, this is the first equation, or the second equation. This is the first, and this is the second equation. We can have a second equation or a third equation from this loop. Moving from this point through this path, we have no electromotive force, so 0 equal I1 R1 plus I2 R2. You have to be careful that when you move in opposite direction for the current, so you will put a negative sign. Okay, this is important rules that when you pass through the same direction as the current in the wire, the current is positive, and when you move in opposite direction as the current move in the wire, you put the value of current negative. And if you have a power supply and you move through a circuit in the same direction as power supply, your value of EMF is positive, and when you move in the opposite direction, your value of EMF is negative. We have many examples on Kirchhoff law, and you have to solve many questions. It's very easy if you follow the rule that if you with the direction of the current or opposite to put the good value or the right value, positive or negative. Thank you. See you later, inshallah. Assalamu alaikum.